Welcome to this presentation today about RILEM Technical Committee TC 258 AAA about avoiding alkali aggregate reactions in concrete, performance-based concept. My name is Professor Børge Johannes Vigum. I will talk about the activities and achievement of this committee for the past 5 years. I am appointed at Heidelberg Cement Northern Europe, and until recently I was an adjunct professor at the Norwegian University of Science and Technology. Starting with the mechanisms behind alkali aggregate reactions. In order for the reaction to occur, you need to have 3 components. You have to have reactive aggregates, you have to have sufficient water in the concrete or high moisture content, and you have to have a certain degree of or amount of alkalis. If you're taking away one of these components, the reactive aggregates, nothing will happen. If you're taking away or lowering the water content, like in indoor concrete, you will not have this reaction. And if you have the alkalis below a certain level, then the reaction will not occur either. The alkalis will be supplied from the cement, but could also come from external sources and even from the aggregates itself, that we will come back to. And in addition, increased temperature will also accelerate the reaction. So what is happening is that SU2 minerals in the aggregates, in the concrete, in the high pH environment in the cement paste, those minerals will start to dissolve and it will be produced the alkali silica gel. And this alkali silica gel is very thirsty, it's absorbing water a lot. We do know about this alkali silica gel when you're buying a camera or whatever, and they are in there to absorb humidity. And that's exactly what's happening in concrete. This alkali silica gel is absorbing moisture, and by absorbing it's expanding, and the expansion forces is strong enough for the whole concrete body to expand. So you could have some expansion of the concrete body, you could have some map cracking, and all this expansion and cracks will of course be bad for this concrete structure, and could also introduce some secondary damage like frost thaw damage, reinforcement, corrosion, and so on. It was Thomas Stanton back in 1940s in California that realized these mechanisms. And he actually did a great job, and he started to introduce test methods. He introduced a motorbar test that later came as ASTM 227. Also, different other countries started to develop different test methods. And back in 1986, Oberholzer and Davids in South Africa, they developed the South African accelerator motorbar test, as later on has been known as the accelerator motorbar test. So it was developed many different test methods in different countries. So it was in a way difficult to compare the different results from the different test methods and so on. So then it was obvious a need for a holistic approach on a global scale. And with that respect, RILEM was the right organization to start to look at these challenges of alkali aggregate reactivity around the world on a more global scale. So back in 1988, the first technical committee of RILEM, TC 106, was established, and that TC mainly worked with accelerated aggregate tests and so on. And then the next TC started in 2001 to 2006, looked into diagnosis and appraisal and specification. And then the third TC from 2006 and to 2014 looked more into performance testing and modeling. And all these 3 TCs were chaired by Dr. Philip Nixon from England, and the deputy chair Dr. Ian Sims from England as well. So they did a tremendous good work during these 25 years of service. And as a main outcome of test methods in this work, it is a three-step testing procedure in RILEM. So we have the petrographic method using the microscope to look at reactive aggregates and so on. That's the AAR1 method. Then we have the second step is the accelerated mortar bar test, putting mortar bars into 80 degrees and one normal sodium hydroxide solution. You got quite quick results of that test. So that's the second one. And then thirdly, you have the concrete prism tests. We have two versions, the AAR3, where the exposure is at 38 degrees, and AAR41, where the exposure are at 60 degrees. And the concrete prisms are stored at 100% relative humidity. So the publications or deliverables from these three TCs by Nixon and Sims. First we had a publication by Springer in 2013 on the guide to diagnosis and appraisal of AR damage to concrete structures. And then after the third TC we had these recommendations published in 2016, RILEM recommendations for the prevention of damage by AR reaction in new concrete structures. And also additionally, we had a very comprehensive petrographic atlas with many examples of thin section micrographs of reactive rock aggregates around the world. So after the third TC, it was realized that we needed to continue this work, and a new application for a fourth TC, the TC 258 AAA, was started in 2014. And that is the main content of my presentation today, to present what we have done. And the purpose of this technical committee is to develop and promote a performance-based testing concept for the prevention of deleterious AR in concrete. And we also stated that there will be strong emphasis will be put on the implementation of the RILEM methods and recommendations as national and international standards. So the committee established in 2014, I had the honor to be the chairman of that committee, and Dr. Jan Lindgaard from SINTEF in Norway was the deputy chairman or the secretary of the committee. We divided the work in this TC into 4 different work packages. So the first one looking into performance testing and accelerated testing in laboratory. The second one about performance testing and laboratory results versus field from exposure sites. The third one looking into the assessment of detailed alkali inventory in concrete, and eventually a fourth one looking into the verification of performance testing. I will go through those work packages a little bit more in detail now. So the first one was led by Dr. Terje Rønning from Heidelberg Cement Northern Europe, and it was looking into the performance testing and accelerated testing and laboratory. First we had a RILEM AR Note document. That is a document that already were published in the previous TC, but we revised that document, which is an outline guide to the use of RILEM methods. In addition, we developed a new concrete prism test called AAR10 at 38 degrees, and we have 2 new concrete prism tests, AAR11 and 12, where the exposure are at 60 degrees. And finally, we developed RILEM AR13 based on a Japanese test approach, where the concrete prisms are wrapped with an alkali solution to counteract against leaching. one of the reasons we come up with RILEM AR10 was that we saw the need to increase the prism size. In a Norwegian research project and a PhD work by Jan Lindgaard back in 2013, it was realized that if the prisms in this was in this size, it was a problem that we got some leaching on the top and the bottom of the prisms. And by leaching, you are reducing the alkali content, and that is not good as a performance test. So as a consequence, now as the AR3 prisms had a width of only 75 millimeters, we are now increasing the prisms up to 100 millimeters, and by that we think we are reducing the leaching and obtaining a more realistic expansion. So that is the new thing with the RILEM 10 method. In the second work package, led by Professor Benoit Fournier from University of Laval in Quebec, Canada, we look into the results from the laboratory, from the accelerated performance test, and what is happening in real structures or real exposure sites. We did establish some new cubes back in 2015 in this TC. Some cubes were cast in Portugal, and they were distributed around the world to different exposure sites, and now we are starting to collect and gain information on the environmental effects of different exposure sites in warm climate, humid climate, colder climate, and so on. So this will be an ongoing activity, but we already have invested a lot in these cubes, and it will give some very good results in the near future. We also had some all blocks study because we had a European project back in 2005, and we were able then now to take cores from those blocks that have been exposed at different exposure sites, and we are doing a very thorough examination of that blocks to see how they behave in the different environmental and so on. And additionally, in this work package has been carried out a very thorough STAR report looking on the lab field correlation. Because it's important when you are testing in the laboratory with accelerated conditions, when you got some expansion results after months or year, but relatively short time, comparing to what's happening in real life in exposure sites. Do we compare apples and pears, or how is it? That is a very crucial and important question. We do know that in the laboratory, if you are accelerating the conditions and you have a higher temperature, you know that if you're taking an egg and putting it into 100 degrees boiling water, you will get a boiled egg after 6 to 8 minutes. If you take the same egg and putting it at 38 degrees, well, then you get the chicken after 28 days. So the outcome in real life compared to the laboratory is quite different if you have accelerated conditions. So we have to take care and look at the effects of temperature. And those are things we are looking into. Then in the third work package, led by Dr. Esperanza Mendes from CSIC in Spain, we're looking into the assessment of detailed alkali inventory in concrete, including internal aggregate release from the aggregate itself, recycling of aggregates, and external supply of alkalis. It has been discussed for a while that it is a potential that the aggregates themselves are releasing alkalis in the environmental of the concrete. So it was developed a new test method, the RILEM AR8 method. We made 2 round-robin tests, and we have now this RILEM AR8 method measuring the potential maximum releasable alkalis from aggregates in the laboratory. So that is a very interesting method but it's very important to tell that this is an accelerated method in the laboratory, and we do need to verify the results coming out from this method and the number itself. In addition, in this work package is what made a star report on the alkali inventory. Alkali inventory in concrete is very complicated. When you're testing concrete prisms like this, well, you are increasing the temperature. You want the humidity to go into the concrete prism for the reaction to occur, and so on. That's important. But we do know that there will be some leaching of alkalis out from the prisms. That's the challenge. So that in order to compensate for that, we sometimes are boosting. That means we are adding alkalis to the system. Also there's some speculations that there could be some recycling of alkalis when they're going into the gel and they're going out of the gel again and starting to react. So that's a complicated question as well. And we also know that there will be some concentration of alkalis in the top of the prisms and so on. And then there have been quite some discussions if all the alkalis in the system are available, or are some amount bound in the system and not participating in the reaction. That's an uncertainty. And then it's this uncertainty if the alkalis, or if the aggregates themselves are releasing alkalis into the system. So having a good overview of the alkali inventory is very complicated. So this is the challenge that was looked into in this work. But as I said, we are measuring now the potential alkalis released by the aggregates in an accelerated test. But it is very important to verify this potential alkali release with what is happening in real concrete or in performance testing in laboratories to start with. And we also need to validate a test method for alkalis released by the aggregates. So this work package was actually started in the middle of the TC after 2 years or something. And it has been led by Professor Klaus Wert from Norwegian University of Science and Technology. And we have not kind of finalized this work, so this work definitely needs to be continued in this verification, which is very important. So in this 5 years period, it has been a very exciting time to meet all these people and work with all these people. We have had 12 physical meetings during this period. Fortunately, we have been able to travel these 5 years, so we have met at 12 different. So we started with the first meeting in Oslo in October 2014. We had the second meeting in spring 2015 in London. We had a field trip and a workshop, and the third meeting in Ottawa and Toronto in September 2015, and the fourth meeting in Paris in March 2016. Then in cooperation with the International Conference on Alkali Aggregate Reactions, ICAR, we had our fifth meeting in São Paulo in Brazil in 2016. And the RILEM week in Lyngby, Copenhagen in Denmark in August 2016. We also used the opportunity to meet, to have the TC meeting there. The seventh meeting we had in May in Stockholm 2017, and the eighth meeting in Vienna in November 2017. We had a ninth meeting in 2018 in Reykjavik, Iceland, and a 10th meeting at EMPA in Dubendorf, Switzerland in 2018. Finally, we had the 11th meeting in association with the RILEM Week in Rovinj in Croatia in March 2019. We had kind of not a full TC meeting, but a working meeting at LENEC Lisbon in October 2019. And then finally, the 12th and final meeting was in Delft in the Netherlands in December last year in 2019. there have been many participants in this TC. We have had many guests participating, of course, and other people contributing. But we ended up with this list of 48 people, which is the official list of members of this TC. As you can see, we have many people from Canada, but also from US, and of course a lot from Europe, but also Asia, and so on. So it's been a very, and this is to my opinion, a very good group, and it's the leading scientist on a global scale. So what we have delivered? Well, I have been presenting these recommendations. So we have this RILEM AER note, which is the outline guide to use the RILEM methods. We have made an updated version of that document. And then we have the test methods. We have the RILEM AER 8, which is the determination of potential releasable alkalis. We have this new concrete prism test, AER 10, with a larger prism size. We have AER 11 and AER 12 concrete prisms exposed at 60 degrees. And then finally we have this AER 13 based on a Japanese procedure where the prisms are wrapped in an alkali solution. And all those recommendations were submitted to Materials and Structures in June this summer. So we hope they will be published during the months to come. In addition, we have been working on this state-of-the-art report, which will contain two parts. We have the first part, overview of the alkali inventory in concrete, which has been led by Dr. Esperanza Menendez, and the second part on the laboratory versus the field correlation, led by Professor Benoit Fournier. So this state-of-the-art report will hopefully be finished and submitted during the next months. We also have been presenting outcome from this TC at various occasions. We had this international conference on ASR in Sao Paulo in 2016, where we made an overview presentation of the background of the RILEM TCs and the work we were going to do in this TC. I had a keynote speak at the International Cement Microscope Association in Canada in 2017, when I presented also the background of the RILEM TCs and the work that we were doing in this current TC. We were participating at a conference in Cape Town, South Africa, where we had a dedicated session to this RILEM TC and the work doing. So we both made an overview presentation of the TC, but also more specific results from the various work packages and so on. And then we were participating in the RILEM week in Croatia. So we had also there a separate session on alkali silica reactions, and very many of the presentations there were related to the work being carried out in this current TC. And we were supposed to present at the 16th ICAR, which was supposed to be in Lisbon this summer in June, but due to the COVID situation, that ICAR conference has been postponed to next summer 2021. And we will there present both overview papers of this, the background of RILEM, the history, but also what have been done in this current committee, and also more other papers which will be more specific in the various results from the various work packages. So it's been a great pleasure to be the chairman of this technical committee. I think during these 5 years we can realize now, when we are about to to finish this committee that we have been delivering the suite of recommendations that was promised originally. The state-of-the-art report will be a few months postponed, but it is very close to be finished. And I think it is necessary to say that it has been an enormous effort from the many global leading individuals and experts in this field and how they have contributed in this. And I'm very grateful, because we have to remember that all this work is done on a voluntary basis. So I am very happy at all the colleagues that what they have contributed. And I'm also glad that we have now the contingencies secured by a new proposed TC application by Professor Jason H. Eidecker. Actually, now two new TC applications in this field. So we have the one where Jason H. Eidecker will be the chairman, and the deputy chairman will be Klaasje de Wert from Norwegian University of Science and Technology. Jason Eidecker is from Oregon State University, and that is a TC looking into the framework to assess risk of concrete mix designs with alkali silica reactive aggregates. And second, we have also a proposal from Esperanza Menendez Mendes, where Leandro Sanchez is the deputy chairman, and the title of that TC is Alkali Aggregate Reaction Mitigation. I'm very glad that this work will continue, but it's a challenge that we should not have too much overlap between these two different TCs. But it's going to be interesting to see the development in this field. And just at the end, it's just important to remember that success is failure turned inside out, the silver tint of the cloud of doubt. And you never can tell how closely you are. It may be near when it seems so far. So stick to the fight when your hardest hit is when things seem worse, that you must not quit. Thank you.